Welcome. In this video, we're going to find the final temperature and pressure in an adiabatic process. So let's call this question 9b. So from here, what we're going to do is, first of all, we need to find, or rather, we need to come up with the data that we've been given. And the data that we've been given is the T1, which is 17 degrees Celsius, and also the heat capacity constant, which is equal to 1.4. Then the other thing is the P1, the pressure one, which is 760 millimeters of mercury. So from here, what we're going to do is, we know that this is the process that we've been given, or rather, this is the scenario that we've been given. The question says an ideal gas at 17 degrees Celsius of 760 mercury is compressed adiabatically until its volume is halved. Take the adiabatic index to be 1.4. Calculate the final pressure and the final temperature. So here we know that for an adiabatic, so this is solution. We know that for an adiabatic process, we have the P. This must give us P2 V2 R. And this, we can just transform this into this by simply making P2 the subject, since we want to find the final pressure. So we're going to say P1 V1 over V2, which can also be written as P1 then V1 V2 then power the adiabatic index. And from this information, according to what we've been given here, so our P2, which is the final pressure, is going to be the initial pressure, which is P1 times the initial volume. So the initial volume, let us call initial volume as V0. Then the V2 is going to be V0 over 2 because the volume is halved. So it is going to be divided by 2, so, or being multiplied by half, which is just going to be 0.5 V0. And from this, we are just going to say V0 over 0.5 heat capacity ratio. So from here, we can plug in the values now, where this is 760 millimeters of mercury. Then this and this will cancel, and what we're going to have is 1 over 0.5 times, okay, to the power 1.4. And what we're going to get here when we plug in the values, what we're going to get is 2005.652, which is equal to, which can also be rounded off to 2006 millimeters of mercury. So adiabatic, the temperature are 1, then volume 1, heat capacity ratio -1, that is V1 is raised to that power, and then this must give us T2, V2, then the heat capacity ratio -1. And this one, if we want to make T the subject, we simply divide by V2 raised to the power heat capacity ratio -1, even here V2 heat capacity ratio -1, so that this and this will cancel, and what we're going to have here is T2 is equal to, we have the T1 here, so this one, it is going to be the V1 V2 raised to the power heat capacity ratio -1. So from here, what we're going to do is we're just going to plug in the values, since we know that T1 is equal to 17 degrees Celsius, which is equal to 290 kelvins. And the V1 is equal to V naught, then the V2 is going to be V naught over 2, which is simply 0.5 V naught. So from here, let us just plug in the values, and the adiabatic index, which is the heat capacity ratio, the R, this is 1.4. So here, let's plug in the values now. So we have 290, then times, so this one we put the V here, then the 0.5 V naught here. Then raised to the power 1.4 minus 1. So here, this one and this one, they are going to cancel. All we're going to have is 290. Okay, this is Kelvin. Then 1 over 0.5 times 0.4. When one is subtracted from 1.4. So from here, what we're going to have is 290 times 1 over 0.5 raised to the power 0.4. We are going to get 382.657 Kelvin. And now the temperatures, this is in kelvins, and if we want to convert to temperature in degrees Celsius, we're just going to say Tc is equal to Tk minus 273.15. And here what we're going to do is, so our temperature in degrees Celsius, we are going to get 382.657 minus 273.15. So what we're going to get is 109.657 degrees Celsius, which can also be rounded off to 110 degrees Celsius. Thank you so much for watching the video.